I talk about stream mining or stream classification in the context of when we divide the data into a number of chunks, and each chunk will have a equal size. So, periodically we will update the model. Now, we want to talk about can we do it can we determine the chunk boundary dynamically. So, that I want to talk about now. So, previously we said in this diagram tell you that we have a k number of first k from chunk 1, second k from chunk 2, something like this. And now, if the k is a very large numbers, then what will be the problem? So, I said if your chunk is very big, then there is a possibility that when there is a concept drift happen in the middle, but you may not update the model immediately, you have to wait longer time. So, there is a trade off. If you set the chunk size too big, then you may not react to the changes immediately, or if you set the chunk size too small, then you may there is a possibility that you do not need to update the model, still you will update the model, you will waste your resources. So, here this diagram demonstrates. So, this is our 2-3 years back work, and the guy who did the work, he went to Microsoft. I asked him to stay here, but he does not want. He joined Microsoft as a data scientist, but anyway. So, here I try to tell you that we have let us say we have a chunk size, we set it up 10,000 instance. So, this is 10,000 instance, this is 10,000 instance, this is 10,000 instance, something like this. Now, so in this is a 10,000, this is a 10,000 instance, this is a 10,000 instance. Now, let us say concept drift is happening here. So, then what will happen? Concept drift is happening. So, this is the whole length is 10,000, and then this is a let us say 100 instance. After 100 instance, the concept drift is going on. So, that means you need to update your model. So, if you do not update the model at this point, what will happen? Many of these points here will be misclassified, right. I am showing you this diagram. I am saying this is let us say 1,000, 100 points, and this is total 10,000 points. So, now 9,900. So, there is at this point we should update the model. Now, if we set the chunk size is 10,000, that means we are updating the model here, but we are not updating the model here. So, there is a possibility that many points here in this area will be misclassified by the existing classifier, because existing classifier is obsolete at this point, and we have to wait another 9,900 points. After that, we will update the model. So, in this case, within this area, with the current classifier, the model will not perform well, the model will perform poorly. So, that we try to say when you set the chunk size too large, you may not react to the changes immediately, and then it may contribute larger error. And on the other hand, if you set the chunk size too small, then what will be the problem? Problem is there might be no concept drift or no changes, but still you are updating the model, you are wasting your resources. So, there is some work to address that issue called adaptive chunk sliding window technique. So, what do we do in the other people did the work in this area, what they do? Just think about this. So, it basically monitors the error rate of the classifier, and if they see that if the classifier is not doing well, then they will update the model. But how do you know that classifier is not doing well? So, that means you need to provide the ground truth, because you are estimating the error. How do you estimate the error? So, what I am saying here, let us say here you have a bunch of data points, right. So, each data points the model will come up with a prediction. When you come up with the prediction, then in order to estimate the error, we need to know the ground truth of this test data points, right. Once you know the ground truth, then only you can estimate the error. And then if you see the error goes up in this window significantly, then what you can tell? Then you can say that the model is obsolete, you need to update the model. That is the idea here. But this method does not scale well for a big data area or a stream, because it is a fully supervised, and in the stream there is no way you can provide the label immediately. So, here you can see, okay, this animation shows you something I have to explain. Okay, so, here we are saying we take n number of points in the window and try to do the prediction, and then after the prediction we will have a ground truth, we will estimate the error. If the error is high, then we will say we need to update. Let us say error is not that high. So, we are happy with this. So, then we slide the window, and then we try to determine if there is a change happen or not, if there is a error is going up or not. So, like something like this. So, now we develop a fully unsupervised model in our case. So, what do we do? Instead of using the error, we are not asking the human to give the label and so on. So, what do we rely? When the test data comes, the ensemble will come up with a prediction, right. So, when ensemble comes up with the prediction, it comes with a confidence. So, the idea is this. So, let us say points are coming like this. So, what we will do? The model will, or ensemble will come up with a prediction, right, each of this point. Let us say this is the first point and so on, and the model will come up with a prediction. When it comes up with the prediction, it comes up with a confidence value also in our case. So, each of the prediction will have a confidence value, confidence 1, confidence 2, confidence 3, something like this. Now, in the window, if you see that the model the ensemble has a very high confidence value in a window, then what you can say? You can say that the current ensemble is doing perfectly all right, because each of the test points we have whatever we predict with a very high confidence. But on the other hand, if you see that over time this confidence value is going down, that tells you what? That tells you that model the ensemble is not doing well. Basically, you have to replace or update your model. That is the very high level idea. So, that we try to say here. When the test data comes, the ensemble will come up with the confidence values, and then we do some change detection in the confidence. So, here we have total n number of instances in the window, and each of this instance will have a confidence that ensemble will give you. And in this window, if the confidence value is very high, then the change detection will not find any changes. But if the confidence value is dropping, then we will say in this point, let us say we can say that there is a change happen after this. So, therefore, we need to update the model and then the window will be reset. On the other hand, if there is no classifier is okay with the current, when you do the prediction, we see that confidence value is high. So, at that point we can say that we do not need to update the model. So, basically we will increase the window by 1. So, now the question is, what is the key point? Key point is how do you estimate this classifier confidence or ensemble's confidence. So, that we want to talk about more details. So, recall that when the test data comes, the model has, we want to do the prediction, right, and the model will have some confidence value. How do you estimate the confidence? The ensemble has a t number of or L number of models. So, in this case t number of models, and recall that what we did in the past. So, ensemble, our case ensemble consists of a number of models, model 1, model 2, and then what is the model? Let us say ensemble size is model T, ensemble size is T number of models, and each model internally what does it have? Can you recall? It has a bunch of clusters, right, small clusters, and then now basically what we try to do when the test data comes, each model will give you some sort of confidence values based on the cluster's proximity and the purity, and then we will take the average and then that will be the ensemble's confidence. So, here what we try to say, okay, here we try to say okay, where is the okay. Here we try to say something like this. So, each of the model will come up with a prediction and the prediction will be associated with the confidence values. So, for the confidence we try to say, we recall that we have a bunch of T in the ensemble, we have a T models and each model has a, we keep the cluster information, right. So, within the cluster what type of information we keep? We keep the centroid information and then the quality of the clusters, what we call it in this case purity. I will explain that in a minute. So, just think about this is one particular test data X and this test is covered by this is X is closest to this cluster centroid. So, this is a, let us say this is a H clusters and this cluster is the closest with respect to this. This X is closest to this clusters because this is the, in the model we maintain multiple clusters and one of the clusters, this cluster will be closest to, the X will be closest to this cluster centroid. Now, from this cluster I need to know the classifier confidence values. So, what I will do? I will consider the cluster purity information plus the cluster proximity, the centroid proximity. So, if this point is closer to the centroid, what do you can say? You can say that the confidence value will be high, right. If this point is far in the border area of this clusters, say somewhere here in this is the border area, and this point is part of this cluster, therefore, it will be somewhere here at most or it will be somewhere here. So, now if it is here, then that should carry lower confidence as respect to with this, right. So, that we try to capture it using the two properties, what we call it association and the purity. Association means how close it is from the cluster centroid. If it is closer to the cluster centroid, then it will carry higher confidence values, or it will contribute higher confidence values. And if the cluster has a high quality of the purity, then it should carry higher confidence value also. So, for example, in this case we have total 15 instances, one of them is a basically outlier or noise. So, it is a defined class, red class, and the rest are blue class. So, in that case purity of this cluster will be 14 by 15. So, that type of information we would want to take into consideration when we do the classifier confidence. So, recall that we have a test data comes, and for the test data I need to estimate the confidence values. So, now how I can estimate it? So, I have a t number of models in the ensemble, and in the each model has the bunch of clusters, centroid information, radius information, and so on. Now, what we will do for a given test data points, I will find the closest clusters in that model. Once I find the closest clusters, I will try to determine the cluster's proximity, I mean how far is that point, test point, from the cluster centroid. If it is closer, then it will carry higher confidence value, basically higher probability. And then if the cluster is pure, it will give you the higher confidence value also. So, these are the two factors we can take into consideration.
What's the threshold for your purity?
Purity, we do not have a threshold. So, basically purity will be just do the, here in this case 14 over 15, that way we define the.
I mean, I get that.
Sure. I will explain, I have some math in a minute. Okay, so here just for each testing instance x, I need to determine the confidence value for the ith model, means ith classifier. So, Ci will be calculated by this, confidence value for that classifier or the model will be calculated by this xi dot zi. Zi is the basically the weight that will be calculated from the training data, and hix will be this way we will define it, association times proximity. So, it is basically there are various ways you can do it. This one way we did it and it worked, but there we try to consider the clusters proximity plus the purity, and then final confidence value will be from the ensemble will be calculated by doing the average. So, here I told you before, if this this test point is closest to this cluster H, then we will calculate the proximity will be, if you remember, we have two properties we need to calculate, A association and the proximity, that will be calculated by this. So, closer to the centroid means the association value will be high and pure the cluster is better. So, that way we estimate the HIX. HIX is nothing but the AIX dot PI. So, AI is the association of the cluster, how close is to the cluster centroid, and the purity of the cluster, then it will have a higher values in the confidence calculation, and then Zi is the weight. And now I will explain how we estimate the Zi. Zi will be estimated the weight of the model or the ensembles, I am sorry, weight of the model will be calculated from the training data. So, let us say for each model MI has a bunch of training instances. So, one particular training instance is k. So, we will the same way we will calculate for that training instance we will calculate the AI and the PI, association and purity, and since this is a training instance we have the ground truth, right. So, now we will see if this value is 1 when the ground truth agrees with the predicted values. If the ground truth does not agree with the predicted values, it will be 0. Then we will calculate there the correlation between AI and Zi, PI and the Zi. That way we will estimate the weight after normalizing it. So, here this diagram will tells you more. Let us say this is the one ensemble size is 3 and we have 3 models M1, M2, M3, and these are the clusters we maintain. And then each of this model will have a weight. So, Zi will be this. So, this is the vector, the first one is the association weight and the second one is the purity weight for each of this model. And then the test data comes, test data is this. So, which one is the closest with respect to this test data, this is the closest cluster, right? And for this case, the test data is here in this model, and which one will be the closest cluster? This one. For this, which one is the closest cluster? This one. And then from there, we will estimate the association and the purity for this cluster. We will estimate the association and purity with respect to test data. And these are the numbers you will get. Now, the confidence value will be calculated for only for these two, because there is an agreement. These are the two classes, the green classes these two are saying, and this is a blue class they are saying. So, we will not consider this in the confidence calculation. We are not going to use this because it predicts it's a different class. So, for this what we will do, we will take this value and multiply with this, right. So, 0.52 times 0.85 and then 0.48 times 0.75 and then Z2 case what will happen? We will take 0.41 times this association weight times this, and that way we will calculate, and then we take the. So, this way the final classifier confidence value will be calculated. So, now, so recall that what I tried to say. I tried to say that we have a ensemble will come up with the confidence values, right. So, in this case, in the n number of window sizes n, and we have each of these instances, we will have a classifier confidence or ensemble's confidence. If the confidence value is very high, then we are happy. If there is a confidence value is dropping over time, then we will say that there is a change happens. So, our goal is to detect that change, whether there is a change is going on or not. So, for that we do some change detection algorithm that I will explain now in a minute. So, just think about this. So, there is a concept drift going on in the stream. So, that means you need to update your model. So, that means classifier is not the ensemble is not doing well for in terms of the prediction. So, what will happen? Ensemble will have so, these are the confidence values for the points we are considering, data points. And now, if there is a if you are happy with the classifier confidence, that means classifier is doing well in terms of the prediction, then the confidence value will be high, right. So, if you plot probability density function probability PDF versus confidence values, and if there is a no change means whatever the model we have, that we are happy with that. So, you will see that a lot of values will be very high numbers. So, here in this diagram we try to show you confidence value is before the concept drift, the most of the values will fall into this area 0.8, there is a peak. But when there is a concept drift going on in the stream, that means classifier or the ensemble is not doing well. So, the confidence value will drop. So, in that case what will happen? If you plot probability density PDF versus confidence values, you will see many values will be very small. So, 0.2, the density will be very high. So, that we call it change is going on. So, we want to model these changes using the beta distribution. Basically, we borrow this idea from the statistics. So, main key point is this: if there is no change, then you will see that the confidence value we have here, that will have a very high values in the window. But if you have a change is going on, then the confidence value drops. So, you will see that after concept drift, there is a curve will be something like this. So, many values will be 0.2, 0.3, something like this. So, for change detection, what do we use? We use the Q-sum process from the statistics. So, here the idea is we want to determine whether there is a change happens between this n number of points. Each point will have a confidence values, and here we try to test whether between n at the kth point there is a change happens or not. So, basically classifier confidence drops or not. So, using the Q-sum process. So, in that case what we will do, we will have a kth point, we will have a one distribution here that will be modeled by beta b alpha 0 b 0, and then there will be another distribution, we'll model it here. And if this distribution is significantly different, then we can say that there is a change happens. So, that will be done through this formula x k n, and the k is the point where the change happens, and that will be estimated by the this log likelihood ratio. And then again we did the experiment for our data set. Forest cover and PAMAP is an activity data set. If you are running, walking, these are the classes we have. And ECS minor is our previous approach, and this is the ECO, our new approach, where we show that in many cases ECO is doing better than our previous work. But again, one of the problem with the whole of all this work, that it produces sometimes very high false positive rate. So, do you have any questions so far? No? You have a question? No, you have any question? No? Okay, so we are at the end of the lecture almost, then we will start the hands on. Thanks for your patience, by the way. So, here I will address some of your concern. If the data point is a very high dimensional, then this outlier detection may not work well, that you already pointed out, some of you, that is correct. So, we need to address that issue. So, if please feel free to take the, what is it, pastry and all these items, they are bringing new items, so please take it. Okay, so here we will talk about high dimensional data stream. So far when I talk about stream data, we talk about when you did the experiment, we did the experiment with the low dimensional data points. Now we want to focus on the high dimensional data stream, and we will show you new types of novel class detection mechanism in using the CNN, basically the deep learning. How many of you know deep learning already? Okay. So, I will briefly talk about it. So, now here so far the stream mining or stream classification I presented that focus on the low dimensional data points or moderate dimensional data points. But when you have a very high dimensional data points like all these images, autonomous car will generate a lot of they have a very advanced cameras that captures the images and try to determine the incoming in the road condition. They try to determine whether there is a stop sign or not. If there is a stop sign, then the machine learning will predict it as a stop sign, and that will go to the system, and the system will stop the car. So, their classification or machine learning will be used, but that will be done in real time and so on. So, again this will be a part of the stream data. So, here we try to address the issue in two ways. One is we have a new emerging class during the stream scenario, or novel class we already discussed. And we try to address when you have a limited label data. Basically, you may have only few data points when you train your model. So, how do you want to address that issue? So, you already understand that how the novel class may emerge. So, for example, this diagram tells you that in the x-axis represents timeline, y-axis represents class, right. So far, we see our model has been trained with the class A, class 1, class 2, class 3. So, these are the instances are coming like this, and then all on a sudden after time unit 400, novel class, the class 4 is emerging. So, that will be treated in our case as a novel class. So, that we already know. Now, we are talking about high dimensional data points. So, here I just to try to motivate you what problem setting we are trying to address. So, let us say you train your classifier with the training data, the class level we have charge outdoor image. These are the each image we want to predict the class level. Class level is in this case it represents, this image represents charge outdoor, this image represents dining room and so on, and the data are coming like in this manner. In this case, one after another the scene or the images, and we want to do the prediction. So, we are successfully predicting and so on. Now, all on a sudden you train your classifier so far with the charge outdoor and dining room, and all on a sudden the bridge image pops up and the conference image pops up. Then in this case, in our setting it will be treated as a novel class. Is it clear what I am trying to say, problem we are trying to solve? So, we train our classifier with only say 2-3 classes levels, charge outdoor and dining room, and then stream data are coming, in this case stream images. So, we try to predict those images, and all on a sudden the bridge image pops up in the stream. So, our goal is to identify that this will be a novel class, but we may not be able to say that this is a bridge. Our model will tell the system that we are getting a new image, we cannot identify what is the label, but we can identify this might be a brand new class. Why don't you give a label? Something like this our model will do. But if you use the typical previous machine learning technique, the way the traditional machine learning technique, they will identify this bridge class either a dining room or charge outdoor, something like this, misclassified into existing class. Okay, so then, so here we already criticize this is our old work I presented you. So, this is I don't want to need to tell you again. And for this case, when you have a high dimensional data like image data like fashion MNIST, this is a standard data set, a lot of computer vision area people use. So, this has a, let us say this is a, so this is a bunch of novel class instances, and they share the similar characteristics with the existing class and so on. So, if you use typical our old technique cannot identify this novel class from the existing class. And then this part I also covered it, ensemble based technique and how we do the training and testing. So, now okay, now we are going to model our data points using a Gaussian distribution. So, we assume that each existing class will have a number of Gaussian components, and each component will be known as a prototype. A novel class could be regarded as a different distribution compared to the existing one. So, let us say you have a car class, car images. There is a Toyota car, there is a Honda car or Lexus. So, each car, each model will have we will build multiple prototypes or multiple clusters, you can think. And each prototype can be modeled as a Gaussian distribution, that is I am saying here. So, now when test data comes and test data represents some novel class instance, in that case this novel class instance will have a distribution, and that distribution will be significantly different from the existing class distribution. That is the idea here. And the prototype is an important concept, we are going to use that keyword, so remember it. So, prototype, each component will be treated as a prototype. And here we just to try to tell you what is Gaussian distribution. Gaussian distribution is nothing but a normal distribution you can represent with a mean and variance. So, here in our case we assume that when we existing class can be modeled as a bunch of Gaussian distribution or prototypes. When that novel class instances emerge, their distribution will be significantly different from this existing class prototype or existing class distribution. And in our case, in the past we try to do the ensemble based learning and update the model. Here we will update the model in an incremental way. So, when the novel class instances are detected, I will tell you that part later. So, since we focus on the images, so we will use CNN in a minute, convolutional neural network. So, here the prototype means class characteristics distribution. Each class will be regarded as a Gaussian mixer distribution, and each prototype will be regarded as the mean value of a Gaussian component of each class. So, just think about this is a particular car class, and this car class may have many images. So, for a subset of image, so let us say this car class has 100 image, and then from there we may build 4 prototypes, and each prototype will represent one particular Gaussian distribution, but all these 4 prototypes will represent the car. When the novel class emerges, our goal is to say that this their distribution will be potentially different from the existing class prototypes distribution or prototypes. And then here for each class we maintain an ensemble of prototypes as a classifier. So, think about for car class I am saying we will maintain 4 prototypes. So, you can think about each prototype will serve as a so those 4 prototypes together will serve as a classifier in our case. And when the novel class instances emerge in the stream, so we can once we detect it, then from there we can create new prototypes, basically new clusters with the Gaussian distribution. And then there is also a possibility that new existing class instances may emerge over time. So, we may need to handle the concept drift also. So, here is the bigger picture what I try to say. So, we have let us say at the beginning we have some training data. So, we build I say we want to build the prototypes, right. So, for each class exemplar set means for each class we will take some samples and then build the prototypes. And for the prototypes we apply a first CNN layer, as I will explain that CNN layer in a minute. Basically you take the image and then apply a bunch of filters and then flatten it and produce some flattened result, and that way we build and then we apply the clustering algorithms type of things and incremental clustering and build the prototypes. So, for example, here existing class is class 1 and class 2. The idea here is we will have a bunch of training examples, and then from these training examples will be fed into the convolutional neural network CNN, and it will each of the image, let us say 100 by 100 dimension, and after CNN it may map into a lower dimensional space after flattening it. So, 100 by 100 means what? What is it? 10,000, right? We can map into let us say 50 dimensions after flattening it here. And then we apply the clustering algorithm, some similar to clustering. So, build some prototypes for each class. So, this is a car class, this is maybe say truck class, or this might be say conference class, something like this. And then once we build the prototype, so we keep those, and now test data comes. Test data means test images will come and it will go through the CNN again. So, that way we map into the lower dimensional feature space after flattening, and then we try to determine whether it belongs to any of this class 1, class 2, those are existing class prototypes or not. Basically, again the same way in the past, how do you determine that when the test data comes, whether it belongs to the existing class or not. So basically, we calculate the distance if it is very closer to covered by any of the cluster centroid. Cluster. If the distance between the point and the cluster centroid it is smaller than the radius, then we say that it is part of that cluster. So not exactly same, but similar idea. So we will try to determine whether any of this exists incoming test data is covered by any of this existing class prototype or not. If it is not, then we call it might be a potential novel class, so we will buffer it. And if it is covered by any of the existing prototype, then we will classify accordingly. And when the buffer is full, then we will ask the human to give the label. But there is a possibility in this case, when human provide the label, some of the instances may belong to the novel class. Basically, is not part of the class 1 or class 2, it is a class 3 novel class. Or still it may be a part of some of the existing class. So then we need to update the model. So here we do some sort of incremental learning. So we'll talk about those in details in a minute. So keep in mind, we do buffering. Here we'll need to say how we determine the novel class, and then how we do the incremental learning. But before that, I need to talk about more details about the CNN. So in this diagram, again, when we have a training data points, we take the training data points and go through this CNN layer. Higher dimensional data point will be mapped into lower dimensional, not lower dimensional, it will be mapped into fewer dimensions by using CNN. And then from there, we build a bunch of prototypes for each class. Each class we maintain multiple prototypes. And when the test data comes, it will go through the CNN layer and produce the CNN output or the flattened space representation, some sort of representation, and then it will compare with the existing class prototypes. If it matches well in one of the existing class, then it will be identified as a existing class. If it is not, then we buffer it, and then here we have a novel class detection mechanism we will explain in a minute. And once we buffer it, if the buffer is full, then we will ask the human to give the label, and once we have the label, we will need to update the prototypes and build new prototypes, because some of the novel class may emerge. So some instances may form a novel class. So in that case, we will update we will create a new prototypes. And if it is a concept drift, then in that case, new prototypes, the existing prototypes may need to be updated. So we'll talk about these two issues in a minute, the novelty class detection and incremental learning. So in a nutshell, the block diagram is train the model on the training set, establish prototype and network, and then when the test data comes, we'll do the prediction, and then in that case, we do the novel class detection, and then we do the incremental learning. So let me explain those in details in a minute, but before that, I want to tell you a little bit the CNN layer. So in this case, this is what type of image? Some of them represents dog, some of them represents car, some of them represents cat, and it goes through each of the image will go through the CNN layer, convolutional layer. It consists of multiple convolutions, and each one we apply filters, and then eventually it will be flattened into it will be this image. Let's say the original image is so original image 100 by 100. So it means it's a very high dimension, right? What you pointed out, 10,000 dimensions or pixel values, and if it RGB 3 times 3, and then CNN. Once you apply the CNN, it may be converted into, let us say, okay, it is converted into, let us say, 100 pixels after not pixels, after converted we end up with a, instead of 10,000 dimension we end up with 100 dimensions. So, now every class we take n number of samples and that will be represented in that flattened space like this 100 dimensions. And what we do for each class we maintain multiple prototypes. So, I will explain that in a minute, but keep in mind that when the image comes it will go through the CNN layer and it will be flattened into a, after flattening it will convert it into this, they call it feature vector. This is the feature map we will generate. So, each image now will be represented by fewer dimensions. So, then so for that what we do, how we can do it? So, this is the idea how this is a background material. So, convolutional layer means a CNN is a neural network with some convolutional layers. A convolutional layer has a number of filters that does the convolutional operations. So, let us say you have a 6 by 6 image like this and I apply filter 1 like this. So, here the filter 1 is basically try to capture all these diagonal ones, and here we try to capture this filter 2. So, if I apply the filter 1 in this image, what will happen? So, these are the basically using neural network we try to learn those, these we call it weight, we try to learn those weight also. Okay, so, if I apply this filter here in this original image, what will it will produce? From 6 by 6 we will end up with a 4 by 4 images like this. Okay, so do you know how I get this? No? Okay, so you apply 1 times, if you multiply this first cell left to right, right. So, 1 times 1 plus 0 times minus 1 plus 0 times minus 1 plus second one, second row 0 times, what is the weight? Minus 1 plus 1 times 1, what is the third one? 0 times minus 1 well, let us say all of 0 plus 1 times 1. So, it gives you 3. So, that way we do this. So, then this window will be shifted by this one. That way from 3 by 6 by 6 we will end up with a, so this case we will end up with minus 1 for if we apply filter 1. Then it will be shifted by 1 and that way it will be 4, you will create 4 by 4 image like this. So, this is one filter. Then on that on the same image we can apply filter 2 and produce something like this. So, each filter will be applied to those original image and produce bunch of feature map. So, if I apply the 6 by 6 image to filter, it will produce 2 4 by 4 images. And then what will happen? So, in the original case, so this way you can see original image 36 pixels will be converted into 4 by 4, 16 pixels. So, now for this case the main power comes this way. So, I will take this 9 pixels and connect it the weight. So, let us say 3 will be produced in this case from only from this 9 pixels, right. Okay. Only from this 3 will be produced from this 9 pixels. So, that will be, we will assign some weight. So, in this case this we will use this one, and then this one will not be connected, then maybe 7, which one, 1, 2, 3, 4, 5, 6, 7, this will be 7, position 7, 8. So, this will be 7, 8, right. So, this will be connected and 9, and then the rest will not be connected with 3. And again this 3 you have somewhere, there is another 3 here, where this 3. So, that way it will be connected with the other pixels. So, that way only connect 9 inputs, it will not be fully connected. So, fewer models, fewer parameters will be used, and then the weights will be shared. But the key point is this. So, when the image comes, so the whole CNN, what does it do? It takes it applies a bunch of filters and then applies maximum polling. I will explain in a minute what is maximum polling, and then this process can repeat many times, and after that we will flatten whatever we get, and that will generate a vector, and that vector size will be smaller than the original image, and that captures a lot of localized features, especially for images. And then in case of image classification, typical image classification, so you can think about this will be flattened, right. So, this will represent the input features, and then this will be a fully connected layer in the neural network, and the top one will be all these image labels, cat, dog, lion, something like this. So, what is maximum pooling? So, that I want to explain. Maximum pooling in this case, just think about this, you filter, you create feature map for some reasons that Shiab, we need to fix this, I do not know why. So, this all this minus means -3, -3. So, here if I apply the if I apply the polling here, it will produce, let us say 4 by 4, I will apply the polling 2 by 2. So, we will take this grid and from there find the maximum value, from here that is called maximum polling, and here find the maximum value. So, it will produce what? So, for that area, what is the maximum value? 3, right. In this case the maximum value is probably 0. So, this way, if you have original image like this bird, and after doing all this filtering and then subsampling or the polling, you will end up with a small image like this. So, what is the benefit of doing this, reducing the dimension? That way we need to do, when you do the classification at the end, you will connect it with the fewer parameters need to learn. And CNN compresses a fully connected network in 2 ways, reduce the number of connections, share weights on the edges, and maximum pooling further reduces the complexity and so on. So, the key point from our case, we are saying we take the image and apply this CNN and maximum polling many times, and then after that we flatten it and generate in our case a flattened vector, but that will be a very lower dimension as compared to the original image. In our case, we don't do this. We just take, after flatten, we take the representation and use it for our own purpose. Is it clear? In a typical machine learning or classification case, after flattening it, then it will be connected to fully connected neural network and do the prediction with the cat, dog. So they do the training and forward network, backward network, back propagation, all this, learn the weight, all this weight will be learned here, and there is also in the convolution there will be weight we need to learn. But I am saying in our case, we don't do fully connected layer. Once we have this from the image, after flatten it, we have a reduced dimension, then we use it for the prototyping purpose for our case. So again, recall that we take the images, a bunch of images per class, and apply the CNN many times, and then we flatten it and generate a vectors in the feature map, feature vector, and then for every class we will have a number of samples like this, and then we build the prototype from there. So do you have any questions so far? Okay, so now we use deep neural network architecture with the convolutional layers for a given input x, the image, in our case maybe, or the text. The output of the network will be denoted by this. X is the input and the theta is the network parameters, basically all this weight in the neural network, and then it will produce the feature. Fs is the feature representation that we want to get. And for every class I, select a small set of instances di from the original D and from the exemplar set Zi, and then those from there we will build the initial prototype. So again, when the test data training data comes, it will always go through the deep neural network, and we construct the given x. We just learned already, if it is a training process, then we learn the theta, but if it is a test case, then it will give you the f. So now from there we try to build the prototype. So here we are saying for every class we build a number of prototypes, and each prototype will be denoted, will have this, will maintain this status characteristics or this values. So mu is the mean value of the instance of class I, and the D is the distortion we keep track, and the weight of the prototype, how many instances we have there, and all the all the examples raw data we have, we keep track of here. So how we calculate the mean, mu I, basically we take the fx theta representation, flatten space, and take the calculate the mean. So it's nothing but the mean, and then the di is the distortion we calculated like this. How far is it from the prototype centroid? And then one of the problem we observe in this process when you construct the prototype, let's say this is the blue class instance and these are the yellow class instance, right? In the original space, this blue class instance is very close to the yellow class instance as compared to this blue class instance. But intuitively, what do you expect? You expect that blue class instances should be close together because they are coming from the same class, and this yellow class instances, they are coming, yellow class and these two instances are these two instances represent two defined class. But if you calculate the distance between these two is smaller than the distance between this, which coming from the same class. If you do this in the original space, you have this problem. So what we try to do in the prototype separation, try to learn this distance somehow, so that same class instances will be close together, and then the dissimilar class instances will be far away. So, for that we are using some in the loss function we try to incorporate this. So, here the tau is the interclass distance and the gamma is the intraclass distance, SSXP is the indicator function. If it comes from the same class, it will be 1, and if it is a different class, it will be -1. So, what I meant is this. So, recall that what is ij? One important point is this: when I say prototype Pij, I indicates the class level index, that means it belongs to the class Y, and the jth is the, what is the j? J is the prototype index. So, j is the prototype index, so it is the jth prototype in that for the ith class. So, here we try to say the, when you have a test data comes, I will calculate the distance from the ith class and the jth prototype. So, this is nothing but the distance between the, in the latent space or the learned space or the flattened space, x theta whatever we will learn it from the after CNN. So, that distance, I mean with that representation minus this mu ij. What is mu ij? Is the ith class jth prototype, right. So, from there I could calculate the distance, and that distance, if it comes from the same class, what do you expect? If it comes from, if x comes from this ith class, then that distance should be smaller. If it comes from the not ith class, this point, then it should come from, the distance will be higher. So, here we try to say if x sp is the same class, that means in that case it will be tau minus gamma. This distance should be prototype and the whatever the point we are considering, that distance should be smaller than tau minus gamma when the point comes from the same class. When the points come from the this x points, x is the point, right. So, if it belongs to the prototype P, then this value should be smaller than this. If not, then this value should be greater than this, and the loss function we try to basically minimize the whole expression like this. And this is for overfitting, we use this, but the main loss function is this gamma minus this. And then now when the test data comes, how do you want to predict? We want to predict whether it is a particular prototype it belongs to not. So, it belongs to a prototype Pij will be calculated by this. We will say the point, that data points neural network representation fx theta minus mu ij if it belongs to the class I. If that is the case, then this distance should be small. When it belongs to the prototype Pij given x, we will estimate the probability like this. And then this value is for normalization purpose. And then we just sum it up over all the k, if the yi has a kth number of prototypes. Then overall our loss function is this: we try to minimize the classification loss, classification error, and then we try to minimize the this is what I call regularization error, or basically the prototype loss, prototype error we want to minimize. So, these two will be combined together. So, when the, so again recall that the higher level picture is you have the image comes, you apply the CNN and then flatten it and produce fx theta, right. And then you have, for each class you maintain multiple prototypes, and those prototypes will be represented by mu those values, right, Gaussian distribution. So, now now we are we are in the stage where we want to discuss the incremental learning. So, if you remember here, so I am almost done. So, another 10 minutes at most. Then we will go to the hands on, and then you have a lunch break. Today lunch break will be at 1:15, right? So, you can take some more stuff that's from here. Okay, here okay, so here what I meant this. Okay, so we have a exemplar set, and we take some examples for each class and go through the CNN. It produces flattened space fx theta. Then we apply, from there for each class we build some prototypes using the mean. At the beginning, let us say we will randomly select for each class some points. So, class 1 we have say 200 points, we will randomly select and build one prototype, and then again we will randomly select another 200 from class 1 and build the prototype using mean, and same thing for the class 2. And now when the test data comes, we will map the each test data points pass through the latent space, we convert it into fx theta, and then we will see it is covered by any of this class or not. So, basically there is a threshold based approach, and if that threshold is if it is not part of any of these clusters, not very similar to the cluster, then we buffer it, we call it novel class, and if the buffer is full, then we will ask the human to give the label. Once human gives the label, that means we have more, that means we need to create a, so this this might be a, the human will give a label on the say prototype example class 3. Class 3 happens is a novel class. So, in that case for class 3 we need to build new prototypes, because we build prototypes only for class 1 and class 2s. So, now systems will predict some instances as a novel class, and then human will give the label. Human will say some of the whatever we predict as a novel class instances, most of them belong to the human will tell you that this belongs to the class 3. So, in that case those points we will take and build the new prototypes after, and then once we build the new prototype, there is a potential problem may happen, because before we train the, this is nothing but a network architecture, right, all these weights will be assigned. Now, when you build a new prototype, that means there is a possibility we need to update the network this weight, and once we update the weight, that means there is a possibility some of the existing class prototype needs to be merged or deleted, those type of things may happen. So, that we will take care of it here. Okay, so here we said when we create a new prototypes from the novel class, that may trigger the current network structure needs to be updated, and then that may trigger that some of the existing prototypes we need to merge or delete it. So, here what I meant is this. So, when the novel class instances emerge, then we may need to create a new prototype, and that may then we may need to update the theta parameter in the network, basically update all the weights. And once we update the weight, there is a possibility that some of the existing prototypes, some of the existing classes prototype needs to merge or deleted, those type of things may happen. So there is a merge algorithm is going on here.
What is the back
Propagation. Okay, so I never describe it, but when you do so let's think about this is your input, right? So this is the hidden layer, and this is the output layer. So when you do this is a typical neural network. They have an input and output, and in the middle bunch of hidden layers. And now when you feed the input and you produce the output, the expectation is for the given input and when you learn, these are the ages, we need to learn those weights. So first we will do in the neural network called feed forward learning, and then that way we learn all the weight, and then back propagation, where we will update we will once we learn the weight, now we have some training points. You do the prediction using the learned weight, and that predicted value should agree with whatever the true level you have. If there is an agreement, then you are happy with the current weight. If there is a disagreement, that means you need to update your weight significantly, make some changes or adjustment in your weight. So that here basically in the output layer we estimate the error, and that error will in the back propagation will be in the back propagation algorithm, that error will be propagated at this node, and then it will be propagated at this node, it will be propagated at this node, and so on. So that is called back propagation error. And I never discuss, and internally all these things will going on also. And nowadays when you hear the deep learning solves all the problem, so basically they use this type of architecture. Okay, so for experiment we use, so do you have any other question? No? Okay, so for the experiment we use this data set. You can see the data set has a very high dimension. So that I try to address. So it has many cases it has more than 1,000 dimensions, right? Feature means dimension in this case. And for our case, for the maximum prototype or cluster per class, we build 10. And M is the DenseNet as a DNNI structure we use, and M is the 2,000 exemplars we use. So here this diagram tells you that when you use our approach, which is CPE, and if you plot the data points like this, you can see the novel class instances are well separated from the existing class instances. In the original space, the points novel class instances are embedded or you cannot differentiate very well from the existing class instance. But this case, this is the novel class instance, and they are far away from the other existing class instances. And this is the some other baseline approach where it works, but it may not work that well as compared to our approach. And then now I try to do the novel class detection, and I try to say that we want to use only few label data for the training. So when you use less training data, the classification accuracy drops. But when you use more training data for a given data set, you can see that accuracy goes up. But after that, after 20%, 30% label data, the classification accuracy doesn't improve that much. And here we showed you the various data set. The New York Times is the text data set, and these are the image data set. Okay? And then these are the baseline approaches, including some of our old work that some of you pointed out that there is a problem for the high dimension space, which is true. And then this is CPE is our new work. So you can see here false positive is not that high, around 2%, and the false negative novel class instance will be misclassified as an existing class is around 21%. And then for the text, we don't do that well. Can you get an idea why for text we are not doing well? For text, we use CNN. Text for CNN may not be effective. There is another method in the deep learning community developed called RNN, recursive neural network, or LS. So that might work better here. We haven't tried. But I think for text, how many classes we have? For text, we have total where is the number of classes?
Question.
Yeah.
When you did the text, did you use like a word to vec embedding?
Yeah. We use word to vec embedding.
You did, okay.
Yeah, and then apply the. So that's why the dimension is only 300. Because if you use the original raw text, dimension will be 1,000, more than 1,000. So we use probably we use the Google embedding, not the glob. What is it? W2. And then that will give you each word 300 features, and then we converted part document 300 dimensions here. So Wang, how many classes you have here? New York Times?
Most of the dataset has 20 classes. For the New York Times, it has around 50 classes.
50? 15 or 50? 15, okay. Okay. So 15 means if you can get, what is 1 by 15? 6-7%, that means still a reasonable number. Okay, so when you use 5%, so under different training samples, 5% training data we use, CPA achieves 86% accuracy. And then when you use many more training examples, it improves, but it doesn't improve that much. So obviously, more training data you will put, you will have a better results. And then here we just try to show you that our method doesn't have a, in terms of the processing time, y-axis represents time and x-axis represents the data set. You can see our method is not, it doesn't take that much amount of time. Do you know why? Because we offline we convert the data or map into the lower dimensional space, right? Flatten it. So that helps you when you do the testing. You use not the original data, original features. You use the reduced dimensional space. You use it for the testing. So that's why our performance is reasonably better than other approaches. And then in terms of the, so here I just try to show you the same what I tried to tell you before. So initial data set, you train it with the Church Outdoor Dining Room and Bridge comes as a novel class, we can detect it. And then however, if there is a conference room pops up in the images, in our case we cannot detect that in the stream. So similarly, we train it with the automobile, bird, frog, truck, and so on. All on a sudden in the image, horse image pops up. We can detect it, ships, we can detect it. But if we do not train it with the dog, and if dog pops up, our case will not be able to detect that. And in future, we're thinking about potential application of this work. Let's say we learn bunch of, from the images, we learn the car and so on, and then some sign, and then all on a stop sign, and then all on a sudden new types of stop signs are emerging. So we can identify it as a potential novel class using our technique. Okay, so I try to tell you that a deep neural network base technique I showed you that can be used for the novel class detection, and we call it multitask because we do the novel class detection at the same time we do the incremental learning. Basically, we update the model in a continuous manner. And for each class, we maintain multiple prototypes, and we show that our method is outperforming other approaches. And actually, that ends of the lecture, but there will be hands-on immediately, and then after that, there will be a lunch break, and that will conclude today's workshop. You have any question? No? Or you are bored already? No other question? Okay, thank you for listening. So, Wang, you want to go through the hands-on? So, we have three models we showed you. One is the periodically we update the model, that is called ECS minor. Then we have ECO, where we create the decision boundary dynamically, the ECO approach second. And the third approach is the CPE, which is the CNN, convolutional neural network we use. We have the code for all these three, right? Okay. So, and the last code CPE is written in, this code is written in Python, and the first two were written long time ago, so 5-6 years back. So, at that time Java was very popular. So, we have the code was written in Java. So, you need to run in Java, using Java. Yeah, you want to start the code?